Welcome everyone. Today, we're diving into a focused discussion on blisters in non-cyanide zinc plating. We'll explore what causes these defects, how to troubleshoot them effectively, and practical solutions to prevent them. This topic is crucial for maintaining high-quality zinc coatings and ensuring process reliability. I'm Selvaraj Venkatesan from SS Trading, and I look forward to guiding you through these technical insights. Let's take a quick look at our agenda. We'll start by defining what blisters are and how they typically appear in zinc deposits. Then, we'll discuss why non-cyanide baths are more sensitive to blistering compared to cyanide systems. After that, we'll identify the root causes, covering pretreatment, organics, and bath chemistry. Next, we'll outline a systematic troubleshooting approach. Finally, we'll wrap up with prevention strategies and best practices to keep blister rates low on the shop floor. So, what exactly are blisters in zinc plating? Essentially, these are raised bubbles or lifted areas within the zinc coating. They can range from tiny pinhead sizes to larger continuous lifts. Sometimes, blisters appear right after plating, but often they show up hours or even days later, especially after chromating, drying, or baking. What this tells us is that blisters indicate poor adhesion between the zinc and the substrate, weak boundary layers, internal stresses, or trapped gases like hydrogen, or organic inclusions that make the deposit brittle. Ultimately, they signal a process or chemistry issue that needs correction. Now, why is non-cyanide zinc plating more prone to blistering? Well, the cleaning power of alkaline non-cyanide baths is weaker than cyanide baths, so residual oils or oxides can remain and cause adhesion problems. These baths also rely heavily on organics like brighteners and carriers, which, if excessive or broken down, increase internal stress and cause delayed blisters. Additionally, lower cathode efficiency means more hydrogen evolution, which can get trapped under the deposit. Lastly, the chemistry window is tighter. Parameters like zinc to sodium hydroxide ratio, temperature, and impurity levels must be carefully controlled to avoid issues. Let's break down the primary causes of blistering. First, inadequate pretreatment. Things like incomplete degreasing, overpickling, or poor rinsing can leave residues that compromise adhesion. Second, excess brightener or organics. Too high concentrations or breakdown products can lead to internal stress and delayed blisters. Third, bath chemistry issues. Incorrect zinc to sodium hydroxide ratios, low temperatures below 15 degrees Celsius, metallic impurities such as copper or lead, and high current densities all contribute to blister formation. Understanding these causes helps us target the right corrective actions. When it comes to troubleshooting, a systematic approach is key. Start by fixing pretreatment. Verify cleaner strength, temperature, and timing. Control pickling and improve rinsing. And if possible, have parts enter the zinc bath live. Next, check brightener levels using Hull cell tests and apply carbon treatments if excess organics are detected. Then, analyze bath chemistry to restore the correct zinc and sodium hydroxide ratios, maintain temperature between 15 and 30 degrees Celsius, and treat metallic impurities with zinc dust. Finally, review process parameters, reduce excessive current density, ensure continuous filtration with polypropylene media, and check anode area balance to maintain uniform plating. Here are some practical remedies linked to specific causes. For poor cleaning, upgrade soak and electrocleaner cycles, use deionized water for final rinses, and check rinse tanks for oil films. Excess brightener calls for carbon treatment at about 0.25 to 1 gram per liter, dummy plating if needed, and Hull cell tests to confirm levels. Low bath temperatures should be raised to at least 18 to 20 degrees Celsius to avoid cold starts. Metallic impurities require zinc dust treatment, dummy plating at low current density, and removing copper or lead sources from the process line. Weak pickling means analyzing and replacing acid, avoiding overpickling, and using inhibitors on high-carbon steel. Delayed blisters are almost always due to organics or weak activation, so carbon treatment and strengthening pretreatment are essential. To prevent blistering, daily best practices are crucial. In pretreatment, regularly check cleaner concentration and temperature, maintain acid strength, and keep rinse tanks free of oil films. For bath control, analyze zinc and sodium hydroxide levels frequently, maintain temperature within the recommended range, and run continuous filtration. Regarding additives, add brighteners in small, frequent doses, run hull cell panels daily or weekly, and schedule periodic carbon treatments. Finally, in process control, keep current density within the specified window, balance anode area properly, and whenever possible, have parts enter the bath live to ensure good adhesion. Thank you for your attention throughout this presentation. If you have any questions or need further technical discussion or process support, please feel free to reach out. My contact details are provided, and I'm here to assist with any challenges related to non-cyanide zinc plating and blister prevention. I look forward to continuing this conversation and helping you achieve optimal plating results.